Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Our mission impossible is simply to convert some of that hate energy to love energy. As your screen indicates, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. This will be video number 5 on exponent laws and how to use exponent laws to simplify very large expressions such as you see in front of you right now. This is just a continuation from the last video. Let's look at part C over here. We have a huge division bar over here, and we have nothing but dots on top and nothing but dots on the bottom. So we have a huge product on top, like a product string on top, and a fairly large product string on the bottom. And so this will constitute a single cluster, so you don't have to worry about bed mass or anything like that. Everything's been taken care of. The first thing you do is look at the coefficients. Over here we see a -2, -4, -8, 2, -4, and that's it. And then we look at the minus signs. We see a minus sign there, minus sign there, minus sign there, minus sign there. Okay, we don't worry about the minus signs in the exponents. Okay, they're irrelevant for the time being. We're just dealing with the coefficients. And so, we look at all the variables. The only variables that are involved are A, B, and C. And so we conclude that the lowest common base is 2 for the coefficients, and it's A, B, and C for the variables. So in the next step, we're going to look at the coefficients too, or coefficients right now. -2 is already in terms of base 2, so it's a drop down. A squared is a drop down. -4 can be rewritten as -2 to the power 2. Everything else is a drop down. -8 can be rewritten as -2 to the power 3. Everything else is a drop down. And 2 is certainly a drop down. This is a drop down. Let's look at the denominator over here. -4 can be rewritten as -2 to the power 2. And because 4 can be rewritten as 2 squared. And that's it for the coefficients. Everything else is a drop down. So we haven't even touched the variable part of this cluster. First thing you want to do is deal with the coefficients, okay? So now we've got everything in terms of either base 2, base A, base C, or base 2, base A, base B, or base C. The first thing you want to take care of is the minus signs. We have a minus sign here, minus sign there, minus sign there, minus sign there. Okay, the way we deal with minus signs is we treat the minus sign as a base. The base is -1. And we're going to use exponent laws. Over here, this minus sign, we pick up a 1. This minus sign over here, we pick up a 2. Drop it in. This minus sign here, we pick up -2. And drop it in. There are no more minus signs. Let's look at the bottom here. For this minus sign over here, we pick up -2, becomes +2. And we're finished dealing with the minus signs. Next, we turn our attention to base 2, and only base 2. So over here, we pick up a 1, because 2 is really 2 to the power 1. There's the 1 right there. Over here, we pick up a 2.2, which is 4. And over here, we pick up a 3.2, which is -6. And over here, we pick up a 2 to the power 1, so we pick up a 1. Drop it in. On the bottom, we pick up 2.2, which is -4, but becomes +4. And we're finished with base 2. Next, we'll turn our attention to base A and only base A. Over here, we pick up a 2. Over here, we pick up a 2. So we got a 2 plus 2. Over here, -1.2 is 2. We drop it in. And over here, -1.2 is -2. Drop it in. On the bottom for base A, we have -2.3, which is -6, becomes +6. And there it is right there. And -1 becomes +1. And we're finished with base A. And we'll do the same thing for base B. You focus your attention only on base B. Over here we pick up -1.2, which is -2. And there are no more B terms over here, so we go to the bottom. Over here we pick up a 3, becomes -3, and we're done with base B. And the last base is C, so we focus our attention only on C. Over here we pick up a -2, drop it in. Over here we pick up -1.2, which is 2, drop it in. And on the bottom we get -3, -1.3 is -3, becomes +3. And of course 0 becomes -0, no point in dropping anything in there. Why do you want to drop in a 0? I mean, you could if you wanted to. You could drop in -0, won't make any difference. So now, again, we've got a base -1, base 2, base A, base B, base C. And each of these bases have integer strings in the exponents. And now it becomes a piece of cake to simplify this. Over here we get -1 to the power 3. Over here we get 2 to the power 4. Over here we get a to the power of 11. Over here we get b to the power -5. Over here we get c to the power 3. Now -1 to the power 3, 3 is odd, so therefore the result is negative. And there's the negative sign right there. And 2 to the power 4 is 16. And then a to the power of 11 goes there. And c to the power 3 goes there. And b to the power -5 gets downshifted, so it appears on the bottom. So the final answer is -16 a to the power of 11 dot c to the power 3 all over b to the power 5. And we're done. So this complicated looking expression over here, if you run through the process carefully, you will get something very simple at the end, which is easy to analyze. And again, all these answers have already been verified. So you can try some of these problems out for yourself. After all, the only way you're going to become good at mathematics in general is by actually working through a number of problems until you feel comfortable with the process at hand. In other words, with the material that's being presented currently. So practice, practice, practice. I can't overemphasize that. There's no question about it. You need to practice. Let's go on to the next slide. We're going to be looking at Q3, but this time we're going to be using exponent laws to simplify expressions with rational, aka fractional, exponents. All the laws apply exactly the way they have for integer exponents. Nothing changes. Okay? So all the laws apply the way we've been applying them up to this point in time. There's a little note over here, a to the power b over c. I call a, b, and c. I call a the slave. I call b, a is the base, so I call it the slave. B is the rider, because essentially it goes along for the ride. It doesn't have a very, very important role. And I call C the master, because the master essentially tells the slave what to do. Okay, master tells the slave what to do. The rider goes along for the ride. The mission, when you're dealing with fractional exponents, the mission is that the slave must at least try to transform itself to kill the master. Okay, this is like almost like a suicide mission for the master. The master has a death wish. He wants to die. Sorry about being morbid about this, but that's essentially what goes on. The master is in control. He wants to die. He wants the slave to kill him. All the while, the rider goes along for the ride. Okay, let's see how this is going to pan out over here. For part A over here, we have -27 to the power 2/3. We identify -27 as the base, aka slave, and we identify 2 as the rider. There's the B right there, so 2 is the rider and 3 is the master. The rider just goes along for the ride. In other words, you don't pay any attention to the rider at all for the time being. The slave, or the master, which is 3, is begging the slave to express itself as a power of 3. Okay, so the slave tries his best to accomplish that mission. And of course, minus 27 can be written as minus 3 to the power of 3. So the slave managed to comply with the master's wish. Sometimes the slave can comply and sometimes it can't. If it can comply, the master winds up dying. If it can't, the master survives. Okay, now why does the master die? Because now the power of a power law kicks in. And we multiply the exponents together, and 3.2 means that 3 cancels out the 3 on the bottom, and the master dies. So that 3 knocks out the master, it kills the master, and the rider survives. The rider is just an onlooker. He's really not participating in what's going on. This is all about the master and the slave, and the rider goes along for the ride. So at the end, we get minus 3 to the power 2. The rider finally kicks in. And of course, we have 2 negatives, so the result is positive, and 3 squared is 9, so we're good to go. Let's look at the next question over here. We have 32 to the power minus 3/5. We identified 32 as the base, but we also called it the slave. And we identify the minus 3 as the rider. And we identify the 5 as the master. The master talks to the slave. The slave answers as 2 to the power 5. And then you multiply the exponents together and you get 5 dot negative 3/5. The 5's cancel. The master dies. And the rider remains. The rider was negative 3, if you'll recall. So at the end, we've got 2 to the power negative 3. Negative 3 is, of course, a negative integer, so we're going to downshift, and we get 1 over 2 to the power 3, which evaluates to 1 over 8. Okay, so you need a little bit of practice with this master-slave stuff. Let's go on to part C. We have 16 over 81 to the power 3/4. You identify the base as 16 over 81. You identify the rider as 3 and the master as 4. Now, the master talks to the base, which happens to be a fraction in this case. And, of course, the master wants to die. And we know that 16 can be rewritten as 2 to the power 4, and 81 can be rewritten as 3 to the power 4. Okay? Using the distributive product law, or the distributive quotient law, these 4's can both go on the outside, and this becomes 2 over 3 to the power 4 dot 3/4. Okay? Because the 4 over here and the 4 over here can go on the outside and multiply the outside exponent. And we're left on the inside of the brackets with 2 over 3. And the outside of the brackets becomes 4 dot 3 over 4. The 4's cancel, the master dies, and the rider remains. So at the end, we've got 2/3 to the power 3. And of course, using the distributive quotient law, this becomes 2 to the power 3 over 3 to the power 3. And 2 to the power 3 is 8, 3 to the power 3 is 27, and we are done. Let's go on to the next slide. More practice with I call these master-slave problems. So we have bracket minus 8 dot 27 over 125 to the power minus 4 over 3. We identify the slave as this mess inside the brackets. And of course, if we were to multiply 8 times 27, we'd get a natural number on top. So this is really a fraction. And we identify the master as 3 and the slave as negative 4. So the master talks to this complicated slave over here, and the slave tries his best to re-express himself in terms of a power of 3. So the master wants the slave to express itself as a power of 3. We know that negative 1 to the power 3 is negative, so we're good to go with a negative sign inside. We know that 8 is 2 to the power 3, so we can put a 2 here. 27 is 3 to the power 3, so we can put a 3 here. And 125 is 5 to the power 3, so we can put a 5 here. Okay, so if you re-expand this, you'll see that it works out. Because a minus sign to the power 3 is negative, 2 to the power 3 is 8, 3 to the power 3 is 27, and 5 to the power 3 is 125, and we recover the original slave. So that's how you can check that the slave has transformed itself properly in order to execute the task of trying to kill the master. Again, the master can't always die. It depends very much on the nature of the slave. So again, now we use exponent laws. The exponents multiply. We get this mess over here to the power 3 dot negative 4 over 3. The 3's cancel. The master dies. And the rider survives this negative 4. So altogether we have minus 2.3 over 5 to the power negative 4. We can use the flip change sign law over here. This becomes minus 6 over 5. It gets flipped. And then you change the sign of the exponent. And it becomes minus 5 over 6 to the power 4. And then a minus sign taken 4 times will give you a positive. So we put a positive here. And then we get 5 to the power 4 over 6 to the power 4. And if you evaluate 5 to the power 4, you get 625, and 6 to the power 4 is 1296. So this will be the final answer to this master-slave problem. Over here, we have essentially a master-slave problem where the slave involves variables. Same sort of idea. Actually, not the same sort of idea. When it involves variables, it's actually a lot easier. Okay, we don't have to do the master-slave thing for variables. We can just use straightforward exponent laws. Again, you look at this and you see a single cluster. The bases are x, y, and z. There are no coefficients. There are no negative signs, so you don't have to worry about coefficients and negative signs. So we start off by opening up base x. And we look only for base x. We get 3 dot negative 2/3. The 3's cancel and you get negative 2. We only look for base y now. You get negative y dot negative 2/3. Negative 9 dot negative 2/3 is just 4. Or actually, sorry. Negative 9 dot negative 2/3 is 6. So we have y to the power 6. And over here we get 6 dot negative 2/3 is negative 4, and it becomes positive 4 because it's on the bottom. So altogether we have x to the power negative 2 dot y to the power 6 dot z to the power 4. These are all positive exponents, so they remain on top. X to the power negative 2 gets downshifted, so it goes to the bottom. And this will be our final answer. Okay, so you can review that carefully if you want. We'll go on to the next slide. Now we have some more master-slave problems here. F, 81 to the power minus 3/4. The rider over here is negative 3. The master is 4, and the slave is 81. And again, it's the slave that has to comply to the master's wish. The master wants the slave to rewrite itself as something to the power 4. Of course, that something is 3. So 81 becomes 3 to the power 4. Now you invoke the power of a power law, and 4 dot negative 3/4 becomes negative 3. And only the rider survives, the master dies. Okay, because the slave manages to kill the master through cancellation. So at the end, we get 3 to the power negative 3. Of course, negative exponents means negative exponent at the end means downshift. And we have 1 over 3 to the power 3, which becomes 1 over 27. Let's look at G. And this is a little bit more complicated. Again, we have a single cluster over here because there's a dot in the middle. If that would have been a plus sign or a minus sign, we would have actually had 2 clusters. And we'd have to deal with each cluster in turn separately. But over here we have 1 cluster alone. but we'll deal with each set of brackets in turn. Over here, the rider is -1, the master is 2, and the slave is 36 over 49. The slave answers is 6 squared over 7 squared. And if we look at this one over here, the rider is 2, the master is 3, and the slave is -27 over 8. The slave transforms itself as -3 over 2 to the power 3. And you can verify that -3 over 2 to the power 3 is in fact -27 over 8. Okay, we could have done the same thing over here. We could have rewritten 36 over 49 as bracket 6 over 7 to the power 2. I don't know why I chose to write it like this, but in mathematics you have a certain degree of freedom, so you can pick and choose. As long as the method that you're using is legal, mathematically legal that is, then you can go ahead and do your own thing. You don't necessarily have to follow exactly the steps that I use, as long as your laws are being used properly. That's the beauty of mathematics, is because we have latitude. We can be creative. As long as we adhere to the various laws that govern the subject, then we're free to do pretty well whatever we want to do with it. But, you just have to be very careful about what you do. It's a very disciplined subject. So as long as you're disciplined, you're allowed to be creative with the math. So let's continue over here. We can pull out the 2 right there. That'll kill the master, so that we can rewrite that as 6 over 7. The rider survives as -1. And over here, when we multiply the exponents together, the 3 cancels out with the 3, so the master dies, and we get -3 over 2 to the power 2. And now we can use the flip chain sign law over here. 6 over 7 to the power -1 just becomes 7 over 6. And the minus sign squared will give you a positive, so I didn't even write it down. And over here we get a 3 squared over 2 squared using the distributive quotient law. And so again, we continue to simplify. We get 7 over 6, and then 3 squared is 9, and 2 squared is 4. And at the end, you can multiply numerator times numerator, denominator times denominator. If you do that, you'll get a 63 over 24, which then reduces to 21 over 8. Okay, you can cross cancel over here to reduce if you wish. 3 goes into 6 twice, 3 goes into 9 3 times, 7 times 3 is 21, and then 2 times 4 is 8. Whatever you'd like to do. You can either multiply to get 63 over 24 and then reduce, or you can cross cancel over here, your choice. That really doesn't bother me. Let's look at H. It's a similar sort of problem. And let's see what we have. The master, again, we have a single cluster, no question about that, because we have a dot in between. So we're going to be dealing with this term first and this term second. So never try to deal with the whole thing all in one shot, because it's never going to work out. The slave in this case is 25 over 121. The master is 2, and the slave is -3. Over here, the slave is 27 over 64. The master is 3, and the rider is -2. Let's look at this term first over here. The master says 2. 25 can be rewritten as 5 to the power 2, and 121 can be rewritten as 11 to the power 2. Let's go on to the next one over here. The master is 3. 27 can be rewritten as 3 to the power 3. 64 can be rewritten as 4 to the power 3. Again, these 2's over here cancel out the masters, so the master dies. And these 3's over here cancel out the master, and the master dies again. So over here we're left with a 5 over 11, and the rider, which is -3, survives. Over here we're left with a 3 over 4, and the rider, which is -2, survives. Okay, so the master is gone. And over here we can probably use a Flip change sign law to convert those exponents to positive exponents, which is essentially what I wound up doing. So you flip the fraction, change the sign, you get 11 over 5 to the power of 3. Flip the fraction, change the sign, you get 4 over 3 to the power of 2. A little bit easier dealing with positive exponents rather than negative exponents. But again, your choice. There isn't a single way of doing these problems. You have a certain degree of latitude. All you have to know is that the final answers have to be consistent with all the various different procedures that are going to be implemented out there. Okay, the final answer has to be the same regardless of the procedure that's being used. So again, if we continue, now we're going to use the distributive quotient law. Distributive quotient law over here. We get 11 to the power of 3 over 5 to the power of 3, 4 to the power of 2 over 3 to the power of 2, and then 11 to the power of 3. Let me see what I did now. What did I wind up doing over here? Oh, I just brought them together. I did 11 to the power of 3 dot 4 to the power of 2. And all over 5 to the power of 3 dot 3 to the power of 2. That's certainly legitimate to do. And then when you work out the entire numerator, you'll get 21,296. When you work out the entire denominator, you'll get 1125. Again, this can be worked out on your calculator all in one shot. And this can be worked out on your calculator all in one shot as well. And guaranteed that this is irreducible. And of course, this is an improper fraction, and we're not going to convert it to a mixed fraction because there's no point. Okay, let's go on to the next slide. And you know what? We'll call it an over and out for this video. And again, thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from MathLab Tutorials in Toronto.